Before we start, for the audience, if you are interested in discussion or if you have some questions, you can either post your questions to the Bilibili website, or you can join our audience WinChat group by scanning the QR code on the screen now and put your questions to the WinChat group. So we will collect the questions and send them to the speaker. Then speaker will answer these questions after his presentation. Today we are very honored to invite Professor Issei Fujishiro to give a talk. First, let me give a brief introduction of Professor Fujishiro. Issei Fujishiro is currently a professor of information and computer science, Keio University in Yokohama, Japan, and holds an adjunct position at the School of Computer Science at Hangzhou Dianzi University in Hangzhou, China. He received his Doctor of Science degree in Information Sciences from the University of Tokyo in 1988. His research interests include applied visualization design and lifecycle management. Professor Fujishiro served on the editorial board of the Computers and Graphics and has been carrying on with the same position at IEEE TVCG and the Journal of the Visual Informatics. He co-founded IEEE Pacific-VIS as a program chair in 2008 and took on the position of General Chair of Pacific-VIS 2014. He also worked as the CSIG-VIS paper co-chair of IEEE-VIS 2019 and 2018, and the workshop chair of the Pacific-VIS 2018 and the top in VIS 2017. At present, he is the president of the Visualization Society of Japan and a member of the Science Council of Japan. He is a fellow of the GFES and IPSDJ, an honorary member of IEEJ, a senior member of IEEE and ACM, and a 2021 inductee into the IEEE Visualization Academy. This is a very important honor in the field of visualization, and this year, only 4 people in the world have been awarded this honor. Professor Fujishiro is one of them. The top of Professor Fujishiro's presentation today is making effective queries on time-varying multidimensional datasets. So let's warmly welcome to Professor Fujishiro to give a presentation.
Okay, it's okay. My slides. And can you hear me? It's okay?
Yeah, it's okay.
No?
Yeah.
Okay,
yeah.
So let me start. Okay, thank you very much for the introduction, Professor Chen. Hi, hello, everybody. I'm Issei Fujishiro from Keio University, Japan. It's my pleasure to give you a lecture today. First of all, I'd like to thank Professor Yuan, Professor B, and all the other committee members for providing me such a wonderful opportunity. In the past 3 decades, I've been involved in computer visualization research intensively. As you see here, I had many collaborations with a variety of domain experts, which ranges from, sociology, life log analysis, medical sciences, forensics, sports, astrophysics, musicology, geology, seismology, nuclear power engineering, quantum physics and chemistry and meteorology and so on. What I'd like to emphasize here is that my research may be called applied visualization, which I think more than visualization applications, because application visualization include inductive approaches as well as deductive approaches. We can derive many common methods from various applications, and then the induced methods can be applied back to many other problems with similar characteristics. Now, let me state the target problems today. As you know, many phenomena are intrinsically time evolving. Line chart and heat maps are well-known standard techniques to visualize time series data. On the other hand, many phenomena are described in multidimensional variables. As you know, parallel coordinate plots, scatter plots, spider leaf, and dimensional stacking are commonly used to visualize multiscalar data. But it looks like time dependency and multidimensionality have been almost independently treated so far, I think. Therefore, it still remains as a non-trivial problem how to visually explore time-varying multidimensional datasets. Okay. Today, I'd like to pick up a case problem from astronomy, a journal which is called Publication of the Astronomical Society of the Pacific had a special issue on visualization 4 years ago. In the journal, Brian Kent wrote, "Through advanced data visualization techniques, we aim to look at new and potentially unexplored domain of astrophysical data." I think astronomers rely particularly on the value of the observed data visualization and analysis. It's mainly because no one can travel to see real heavenly bodies located far from the Earth. And their only option is to observe and analyze a variety of signals emanating from the distant bodies. In other words, astronomy is just like an ultimate remote sensing. Against this background, this Astro 2020 workshop was held in conjunction with CSIG-VIS to bring together experts from both from visualization and astronomy. Astronomers need modern visual analytics techniques to deal with large, rich, and complex observed data. The workshop publicized a portal site named Visualization in Astrophysics. Okay, so click here. Maybe you can see the website. Okay. So the website started only with 39 papers at the timing of the workshop, but increased the number up to 79. 79 it's shown here at today. Based on the taxonomic analysis of this paper collection, a state-of-the-art report, okay, here, a state-of-the-art report was published in EuroVis this year, which cites 2 papers associated with the case problem and its solution today. It's so honor for me for our paper to be included in the state-of-the-art report in the EuroVis this year. Okay, so specifically today we are targeted at the visual exploration of observable photometric and parametric behavior of lasers. This is very important, hot topics in the field of astrophysics. Okay, let me start with the answer to this simple question. What is a blazer? Which is a compact region at the center of a galaxy with higher luminosity than normal ones. From the center black hole of a blazer, a relativistic jet ejects toward the Earth. And hence the light from the jet can be strongly observed from the Earth. Blazer provide us with the important clue, visual cues, to demystify the physics of the magnetic field inside the jet. Hiroshima Astrophysical Science Center, Japan, has utilized the Kanata telescope to observe the light from blazers, a lot of blazers in terms of polarization, intensity, and color. More specifically, Q and U are parameters for polarization, epsilon Q and epsilon U for their observation errors. I and C represent the intensity and color of the light respectively. Blazer researchers need to analyze time variation of these 6 variables and their correlation. The plane spanned by Q and U is referred to as a Stokes plane, very important keyword for today's lecture. To understand polarization behaviors, Blazer researchers used to analyze time variation of 2 derived variables on the plane. The radial distance is called polarization degree, PD for short, while 1/2 of the polar angle is referred to as a polarization angle, PA for short. Both variables play an important role in describing the potential polarization state. Obviously, from the definition, the Blazer observation dataset can be characterized by their time dependency and multidimensionality. In fact, the observation is long-term, for example, a dozen years or something, and uneven spaced due to the change in observation conditions. On top of that, each variable has different unit and scale, and its values are uncertain with observation errors. These are characteristics of the Blazer dataset to be targeted. When analyzing time variation patterns in a Blazer dataset, astronomers have used multiple animated scatter plots, as shown here. This is animated, which are mutually linked with currently focused dot, highlighted in red for close references. However, it's so hard to understand correlation among these variables from these animated scatter plots. Many dots will give rise to visual character artifacts. Moreover, this method lacks interactivity. To address this problem, my group proposed time tubes, which represent a single data set as an explorable 3D volumetric tube as shown here. It allows interactive exploration of time variation and correlation among the 6 time-dependent variables in a single view. However, even with such a geometric representation, it's still challenging to explore characteristic blazar behavior and identify time variation patterns, especially in long-term multidimensional data set. Therefore, we have developed a novel visual analytics environment named TimeTube-X, which built on the TimeTube representation to realize more sophisticated data analysis of blazars. Okay, so it's a good timing to play a summary video to introduce our TimeTube-X system, actually, which is a web-based visual analytics system for blazar dataset. Okay, this is an accompanying video of our recent paper published in TBCG. Please enjoy.
This video introduces TimeTubes-X, a visual analysis framework for multidimensional, time-dependent observation datasets for blazars. Blazars are in a class of extremely bright galactic nucleus. A blazar ejects a relativistic jet towards the Earth. To understand the physics of the jet, astronomers observe the light emitted from a blazar and analyze correlations of observed polarization, intensity, and color of the light. The main goal of astronomers is to extract and analyze features or patterns in temporal variations of those observed properties. However, it is difficult to identify time variation patterns through conventional animated scatter plots used in the astronomical community. We designed a novel visual analysis system for blazar datasets, TimeTubes-X, which is an extended version of our previous TimeTubes to allow users to effectively explore multidimensional time-dependent observations and locate observable and recurring time variation patterns. The main visualization panel is composed of 3D Tube View, TimeTubes View, and Scatterplots View. We provide various interaction for these views. In the Feature and Pattern Detection panel, users are allowed to specify what to find out with simple interactions. Extraction results are sorted by relevance. Users can decide how many results to show with the suggestion of a distance distribution histogram. The timeline allows users to recognize the temporal distribution of the extraction results. Users can refer to detailed information on a result selected from a collection of thumbnails for the results. TimeTubes-X provides a unique 3D volumetric tube expression for blazar datasets, which was proposed in our previous papers. We express the four polarization parameters as an ellipse, colorized according to the observed intensity and color, and arrange these ellipses along the z-axis in the order of observation. As a result, a dataset is encoded as a single 3D tube instead of multiple animated scatterplots, like this. To allow users to find out observable and recurring time variation patterns from the long-term observations, we've introduced automatic feature extraction methods for well-known blazar behaviors and dynamic visual querying methods for the easy discovery of similar time intervals or time intervals validating a specific hypothesis. In the automatic feature extraction, users can flexibly locate drastic time variations, termed anomalies, as well as common blazar behaviors such as flares and rotations, just by selecting what to extract and setting some parameters. In this video, we apply the rotation detection and check an extraction result in the TimeTubes view. Dynamic visual querying has two options, query by example and query by sketch. In the query by example, users can pick a region of interest from TimeTubes view or Scatterplots view and search for time intervals similar to the region of interest. To make users visually understand the current state of the query, the selected time interval is displayed as another 3D tube, and it is interactively updated when users make changes to the query. In the query by sketch, by detecting drawing speed or pressure in addition to the position of the stroke, users can sketch time variation patterns of 3 variables at once. Additionally, users can assign filtering constraints to each of the control points on the sketch. So, our query by sketch enables users to form a sketch-based query for multidimensional time series data. Our result automatically beautifies the hand-drawn sketch and allows users to adjust it afterward. Users can reuse one of the extraction results as an input for a follow-up query of dynamic visual querying just by dragging a result onto the query specification panel. It implies that users can build a new query based on an existing time variation found in the previous process and iteratively identify more observable time intervals that reflect their intentions. In Query by Example, users can switch variables and modify the time range of the query. In Query by Sketch, users can change the scale, shape, and axis of the query and add further filtering constraints to the query. Our domain experts mentioned that our feature and pattern detection enabled them to flexibly find out characteristic Blazar behaviors and efficiently identify interesting features happening, especially in short time intervals. TimeTubes-X is open source. You can try our system using our synthetic dataset at this URL. Thank you for watching our video.
Okay, so this is a list of primary related journal publications. A full-fledged introduction to TimeTube-X is available from this TVCG paper. The TimeTube representation was comprehensively presented in this paper in a Journal of Physics conference series. Astronomical aspects of the research are discussed in these two papers in a publication of the Astronomical Society of Japan and the Galaxies. This is an additional list of related international conference proceedings paper, including I2P CSIG-VIS, Pacific-VIS, and CSIG International. All right, so for your convenience, let me restart with how TimeTube-X visualizes Blazar dataset. We call 3D tube view for Blazar dataset TimeTube view, okay, where the XY plane expresses the Stokes plane by assigning Q and U to X and Y axes respectively. In this way, a single data sample is expressed as an ellipse whose center coordinates are determined by Q and U values and whose width and height by epsilon Q and epsilon U. Time is assigned to the Z-axis. The ellipse can be colorized according to the observed values for I and C, with reference to the predefined 2D color transfer function like this. We serialize the colored ellipses in the Z direction of time in chronological order and use Cutman-Rom splines to connect them to generate a volumetric 3D tubes. Note that we can assign opacity distribution, which is usually specified in a way that, the more outer, the more semi-transparent, to show the uncertainty of the concentric tubes. Of course, the users are allowed to tweak the opacity transfer function to adjust the Bagu appearance of the tube if needed. This is the main visualization screen of TimeTube-X. The TimeTube view is displayed in the middle, enclosed in by blue rectangle, and at the top there is a menu for manipulating the view. You are allowed to change the background color, switch the camera, and so on. Below the TimeTube view, you can see the temporal profile of the luminosity change, which is panel called Time Selector, where you can manipulate the current data point of interest in the TimeTube views and determine the range of data displayed in the scatter plots at the bottom. By default, the time variation of luminous intensity, namely a light curve, is displayed here. But you can switch to scatter plots between any two variables on demand. In order to design our own visual analytics framework for the Blazar dataset, we have conducted worldwide interviews with several Blazar researchers and then identified the four goals listed here. First, enhance the reliability of Blazar observations. Second, identify flare and rotation. Both are very important characteristics of the Blazar dataset. Number three, locate recurring Blazar behaviors. For number four and the last, validate hypothesis of Blazar blade behaviors. Okay. To meet all of these four goals, we designed a basic architecture of the time choose X, centered around interactive feature analytics as shown here. We intended to establish here so-called astronomer in the loop, which directly stems from the visualization discovery process presented in a Visualization Research Challenge 2006 report. Automatic feature extraction automatically enables to extract the characteristic behavior of the Blazar. Dynamic visual querying makes it possible to find partial time intervals with features that are similar to user-specified region of interest or sketch. Automatic feature extraction and dynamic visual querying are the main topics to discuss in the remainder of this lecture. Before proceeding to the detail, let me briefly mention about the preprocessing called Visual Data Fusion. Visual Data Fusion is a preprocessing function to effectively analyze multiple observations of the same or different Blazars. As you know, the Earth is self-rotating and weather conditions keep changing. So in order to reduce the chance of missing observation, the same Blazar can be observed by different observatories on the Earth. For example, Hiroshima University, Japan has a good collaboration with the University of Arizona in the United States. We have two modes, juxtapose and merge. In the juxtapose mode, we can visually compare multiple tubes in our separate windows. On the other hand, in the merge mode, multiple data sets for the same Blazar are merged into a single tube, which was reconstructed from a dense list of data samples coming from the independent two data sources. In this way, this kind of functionality can address yet another kind of uncertainty embedded in a Blazar observation dataset. Okay, so from here, I'll focus on the feature analysis method employed in the time-to-X. First, let me tell you how to automatically extract features of Blazar dataset. So far, we have implemented the function that automatically extracts subsequences with dynamic time variation and characteristic Blazar behaviors in terms of anomaly, flare, and rotation. Anomaly is defined as a dynamic variation over polarization, intensity, and/or color. Flare in an extreme peak of intensity, while rotation is a dynamic rotation of polarization on the Stokes plane. The automatic feature extraction realizes easy access to subsequences with these features. First, anomaly detection can identify observable subsequences by quantitative screening. We define the anomaly degree as the temporal sum of change amount in polarization, intensity, and or color per day as formulated here. Anomaly detection explores subsequences with high anomaly degrees to identify unusual variation or presage of flare and rotation. Please note that the formulation of the anomaly degree here is a bit different from the one in the TBCG paper because we have updated it to express blazar behaviors more properly. Blazar researchers regard flares as one of the most important behavior of blazar because flares imply that the blazar condition is more energetic than usual and making them want to observe. Flare detection realizes easy access to subsequence with flare and detailed analysis and efficient comparison of them. Left scatter plot for light curve shows time variation of intensity. As indicated by rectangles, blue rectangles, and the associated time to view on your right, flares are obviously extreme peaks of intensity. But no specific threshold on I values cannot be predetermined, which strongly depend on the actual data set. So blazar researchers need to scrutinize subsequences when the intensity is relatively higher. Time to X extracts intensity peaks by parisical peak detection method and consider the detected intensity peaks as flare candidates. Okay, so this slide summarizes the parisical algorithm peak detection, okay, which has two steps. First, for each data samples, we compute the spikeness score S. We have three options to define the spikeness score, but the second option in the middle tends to give the best result empirically, so we have made it our default. With the second option, the spikeness score S is defined by taking the average of differences between XT and the previous K data samples and the average of the differences between XT and the next K data samples. Once we got the spikeness score S for each data samples, the difference between the spikeness score of each data samples and the average of the spikeness score of the entire is computed. Left-hand side of inequality. Okay, and if it's greater than H times sigma S, where H denotes the user-defined sensitivity coefficient, sigma S denotes the standard deviation of all S. If the left-hand side is greater than H times sigma S, it is considered that there has occurred a sudden change and is adopted as a flare candidate. This is the direct application parasical algorithm to detect flare. Next, let me move on to the rotation detection. As shown in the left scatter plot, it's so difficult to identify such time variation from general purpose scatter plot. The time to view on your right will be more helpful for visually exploring such behaviors. compared with the general purpose scatter plot on your left. It seems that rotation can be identified by scrutinizing time variation of polarization angle PA on the Stokes plane, but analyzing time variation of PA cannot address all rotation. It's a very important observation because the rotation center is not always located at the origin of the Stokes plane, especially when there are multiple polarized components in the observation domain, as shown in these examples. This could occur very frequently in the observed data set of blazars. Our rotation detection algorithm was designed so as to detect any rotation robustly, no matter where the rotation center is positioned. TimeTubeX computes the total rotation angle of subsequences whose standard deviation of Q, N, or U are globally large. Then the rotation detection algorithm works as follows. Okay, TimeTubeX firstly computes the weighted means of Q and U, which are considered to be a rotation center of the subsequence. And then the rectangular coordinates are converted into a polar coordinate whose origin is shifted to the rotation center. Finally, it computes the difference of polar angle of two consecutive data samples and sums the differences to obtain the total rotation angle. If the total rotation angle is larger than the user-defined threshold, the sequence will be considered to be a rotation candidate. Actually, we applied this rotation detection algorithm to many data sets. And this is one example, the data set for specific blazar named 3C454.3, which is well known to have severe polarization fluctuations. And actually, as you see here, we could detect 3 rotations where the center of rotation in the yellow dot is not located at the origin of the Stokes plane. These 3 term intervals are consistent with the rotation width flare, which have been reported by blazar researchers in the past. Okay, so let me move on to the central part of today's lecture. Now let me see if I'll focus on the dynamic visual query. The automatic feature extraction is helpful for the location of the characteristic blazar behaviors, as you see. But it isn't helpful to explore time variation patterns. So we propose the dynamic visual query, which allows users to explore subsequences that are similar to a user-defined region or shape of interest without any complex query languages or parameter setting. We have 2 methods for dynamic visual querying. One is query by example. The other is query by sketch. In query by examples, a query is a part of time series, while in query by sketch, a query is a user-drawn sketch. That is the main difference between the 2 methods of dynamic visual query. Before presenting our methods, I'd like to introduce some prior works related to query by examples first. This is our 4 representative prior works related to query by examples. Please note that the first and the second are just for univariate time series data. Number one, which is called time searcher, allows the user to select arbitrary time series data using rectangular widget, as shown here. Number two, constrain the level of similarity based on the speed of input for Roy selection and the distance from original timeline. On the other hand, the third and the fourth are just for multidimensional data. Number three is a method that can define Roy's by tracing parallel coordinate plots. Number four allows the users to analyze multiple scatter plots to select their own region of interest. Next, let me take a look at query by sketch. Number 1, 2, and 3 are just for univariate time series data, while number 4 is applicable to multidimensional data set. Number 1 is one of the very first query by sketch interfaces to search for time series data with features similar to the sketch drawn by the user. In number 2, several distance computation methods for similarity search are compared to conclude that dynamic time warping method gives the most accurate results. Based on this, we decided to employ the same method for time-to-X to compute the similarity. Number 3 processes a similarity computation method that takes into account the ambiguity of the user sketch input. Number 4 is a query by sketch system for a large number of scatter plots. It supports user sketching based on the stored data. To summarize these two slides, although query by examples and query by sketch methods have been proposed for various types of data so far, there is few dynamic visual querying method that is applicable to multidimensional time series data, to the best of our knowledge. This gave us a strong motivation to develop our own QBE and QBS for time-to-X. Okay, so time-to-X query by example allow the user to select a law interactively and find subsequences similar to the specified law. It's helpful to efficiently locate recurring patterns even from long-term data set. The time-to-X QBE consists of 3 steps as shown here. First, the user selects a region of interest from time-to-view or scatterplot view. A selected subsequences will be highlighted in red in both views. Secondly, they can check how the selected region of interest look like in the associated time-to-views and set variables to be considered in the next matching process. For example, when the color variable is not selected, the tube will lose its color and become gray, for example. Finally, they can select the length of time interval they want to search for, the distance computation method, and so on, and run the similarity search to find time intervals with features similar to the selected region of interest. On the other hand, time-to-X query by sketch realizes fuzzy search of patterns. It will be helpful to find the region of interest or test hypothesis. The query by sketch consists of 4 steps as shown here. Let me explain each step one by one. Firstly, user draws a query on a 2D drawing space. They are allowed to assign arbitrary variables to the horizontal and vertical position of the stroke and stroke width. Stroke width is determined by drawing speed or drawing pressure, depending on which input device is used, mouse or stylus pen. The sketch is automatically converted into a beautiful curve so the user can draw without worrying about shaking due to mouse or stylus pen input. They can define at most 4 variables, including time, in a single sketch. This is a very important feature for time-varying multi-dimensional data set. Okay. Step 2, after drawing a sketch, the stroke will be beautified by a cubic Bezier curve. User can adjust the shape and width of the input stroke through simple interaction. Then users are allowed to assign filtering constraints with respect to other variables to each of the points on the sketch, which will making the query more sophisticated. Okay. Finally, they are allowed to set parameters for the subsequent matching in the same way as in a query by example. Okay. As I said before, TimeTubeX adopted dynamic time warping, DTW for short, as a distance computation method for similarity search. When performing a similarity search for a certain feature, it's necessary to compare partial time interval of different lengths, right? Because partial time interval with similar feature are not always of the same length. For example, when considering a flare may occur at the beginning, in the middle, or at the end of the partial time interval, depending on how the partial time interval is extracted. Dynamic time warping is known as a method that can non-linearly expand or contract the time series data to compare the time series of different lengths. And in the related work I mentioned earlier, it is claimed that dynamic time warping can compute the similarity closest to human intuition among several candidate techniques. This slide gives a detailed explanation of dynamic time warping algorithm and the associated data structure. DTW is a method that computes the similarity between data samples in 2 time series data in a brute force fashion to create a distance matrix between the 2 time series data, and then use the distance matrix as a reference to find the path with the minimum cumulative distance. Okay. However, since dynamic time warping is inherently a method for single variable time series data, so we had to extend it so as to deal with multidimensional data for our case. According to Shoki Yakta et al. 2015. We have 2 options, independent and dependent. The independent option uses dynamic time warping to compute the similarity for each dimension, and finally add them together. On the other hand, in the dependent option, the distance is computed considering all dimensions simultaneously when computing the similarity for each data point. Obviously, there is a trade-off between the two options. When using the independent option, the correlation between variables tends to be neglected, while the similarity per dimension is emphasized. On the other hand, the dependent option tends to neglect the similarity per dimension, while the correlation is emphasized. For the Blazor data set, in particular, the correlation between variables is much important. So we adopted the dependent option as our default. Okay, finally, I'd like to introduce a very unique auxiliary function for dynamic visual query. Actually, TimeCubeX allows users to reutilize a selected extraction result as an input for follow-up queries to establish, quick and iterative query refinement. We call this mechanism fact-guided querying. By iteratively updating a query, the users can identify more observable subsequences that reflect their intentions in a step-by-step manner, as shown here, both for query by examples and for query by sketch. Okay. All right. This is a snapshot of TimeCubeX feature analysis interface. When the user uses this panel on your left to issue their query, the histogram of retrieved subsequences in terms of similarity is generated. This gives another view of time distribution of similar subsequences. The user can check the details of a specific subsequence of interest. The section shows an array of time to view thumbnails, where if they want to perform fact-guided querying, they can drag and drop of a specific thumbnail back to the left query issue panel. This pop-up menu is just for input-output control of the analysis results for interrupt or restart of the system. Okay, so it's a good timing to tell you about the one case study results using TimeCubeX. This is the only examples of astronomers' analysis of an actual Blazor dataset called BLLAC, in which query by sketch was applied. The figure on your left is a sketch drawn by the user, a real astronomer. The XY plane of the sketch part is a stroke plane, Q and U. And width of the strokes is assigned to the luminosity. So the query can be interpreted like as the polarization decreases and increases, okay? Decreases and increases. The luminosity intensity, the width of the stroke, increases and decreases, okay? Do you understand this kind of interpretation of the input query? The results of the similarity search are shown on your right, which include the top 12 results. Please take a look at the timeline above. You can see that these patterns appears intermittently through the data. But when you take a closer look at the timeline, they seems to be relatively concentrated in the time period highlighted by the red box. Okay, for example, these 12 representative thumbnails includes the result in this blue box, which can be taken from the red time period here. So we will perform a detailed analysis of this time interval highlighted in blue rectangle as a representative examples from BL-LAC data analysis. Okay, in order to analyze the selected result in more detail, we need to understand the astronomical scenarios for the change in polarization and luminosity. In general, laser researchers make two hypotheses for the increase in luminosity. One hypothesis is that it is due to the increase of the luminosity of non-polarized component in the observed region. The other is that there are multiple mutually orthogonal polarization components in the same region. And the increase in luminosity is due to changes in the luminosity of other polarization components. Actually, we have two interpretations. To determine which of these two hypotheses is significant, we need to compare the time evolution patterns on the lowercase QU and on the uppercase QU. The lowercase QU, which we have seen before, is the uppercase QU divided by I, luminosity, which is the sum of the luminosity intensity of the polarized and unpolarized component as formulated in this equation. Okay? Note here that the polarization degree, PD, can also be expressed as the ratio of the luminous intensity of the polarized component to the overall luminosity intensity I. By intermixing these three equations into a single interpretation, we can deeply think about the difference between these two hypotheses. In case of hypothesis 1, since the change in total luminosity intensity is dominant, I is dominant, the polarization changes in the lowercase QU plane, which is divided by I here, okay? But not the uppercase QU plane. We cannot, observe such a changes. On the other hand, in the case of hypothesis 2, the polarization changes in the uppercase QU plane as well, surprisingly, because the increase in luminosity of another polarization component decreases the apparent luminous intensity of the polarized component, and then also decreases the uppercase QU value and accordingly PD value. Okay, do you understand what the difference between these hypotheses? Yeah, actually, in any good visual analytics systems, so we are expecting to execute what if scenario analysis very effectively. Okay, based on the above consideration, in the time tube X, we juxtapose the two-phase plane of lowercase qu and the uppercase qu in the system. As shown here, the luminosity change and polarization are inversely correlated for both planes. The same is true for a number of other time intervals within the highlighted period. Therefore, we concluded that we should support hypothesis 2, that is, the anti-correlation between luminosity and polarization in this period is not due to the increase in the luminosity of the non-polarizing component, but due to the presence of multiple polarized components. To be honest, in previous studies, it was already found that the polarization and luminosity tends to be globally uncorrelated during the highlighted period, which is detailed in this paper. But using the proposed method, we are able to empirically identify patterns of short-term variability with such a specific characteristics that were difficult to confirm only using existing methods. Okay. So in conclusion, we have presented a web-based visual analytics environment named TimeTubeX today for the detailed and sophisticated analysis of Blazar dataset. The proposed feature analysis framework allows the Blazar researchers not only to easily locate observable Blazar behaviors, but also to efficiently find short-time variation patterns that have not fully been confirmed with a traditional method. The employed methods are applicable also to other time-dependent multidimensional data sets in various domains, I believe. As one ongoing topic, we have tried to incorporate a data clustering functionality into the system to identify the universality embedded in a long-term Blazar dataset. But very sorry, since a related paper is now under review, I really hope that the detail will be uncovered somewhere in the near future. Okay, many thanks should go to my collaborators and students. Finally, I'd like to acknowledge our sponsors, Max and JSPS. As the video said, TimeTubeX is an open source code and freely downloadable from this site. If you got interested in from my talk today, please download and try it. Any comment from you would be very welcome. Okay, so this is the end of my lecture today. Thank you very much for your kind attention.
Okay, thank you very much for your wonderful presentation. Now there are some questions from audience.
Yeah.
Some from the Bilibili and
Yes.
some from the Zoom platform or some from the WinChat audience group.
How many in total?
That's a few questions.
Yeah.
So the first one, he say this is a very impressive visualization of all the 6-dimensional time series data by pairing two related dimensions in such an innovative way. So I don't know much about astronomy. I don't know much about astronomy, but I wonder what design can be used if we have one or two more dimensions. That's
okay, so there, you know, the question I would like to clarify the applicability to other data set or within the astrophysics application. Which? Actually, as I said before, the salient feature of the querying systems adopted in the time tube X, it lies in its applicability for the data set, which is time-varying and multidimensional. So, yeah, of course, depending on the target data set to be visualized, so we need to have some pre-processing to define some feature in quantitatively. But after that, we can apply our methods so as to handle your own application, I believe. Yes, especially, so the important thing is that we, in order to, build query by sketch, for examples, we need to detect some trajectory which shows the correlation between two variables embedding in a multidimensional time-varying data set. Okay, once we succeeded in derivation of this kind of trajectory in the parameter spaces, so the query by sketch employed in time tube X could be applied to your own data set. That's my suggestion.
Okay. Okay, thank you very much. So the next question is how to aggregate data sets with the same goal from many different sources and perform a cross data set analysis.
Yeah.
Yeah.
Yes. So, right. So let me. Okay. So let me go back to the visual data fusion. Now, actually, by taking advantage of the juxtaposed type visual data fusion, we can compare many sources whose target is the same Blazor data set. Some data set have a very dense sampling interval. On the other hand, the other data set contains a sparse set of data samples, but the latter could be more accurate in terms of the observation quality. So we have many strategies to intermix this kind of data set into a single data set to be visualized. Actually, this kind of things belongs to our typical ambiguity problems in visualization and visual analytics. Yeah, actually, so if you are interested in, please consult our paper, which was published in CSIG International and CSIG-VIS, IEEE CSIG-VIS 2018, where you can find more details on the potential applicability of our method for other data set, I believe. Is it possible to be answered to your question?
Yeah. Okay, thanks. And also, next question is normalization and polar coordinates options enable fuzzy pattern search.
Yeah.
So why did you choose these two metrics? That's the question. Yeah.
Okay, so as I said before, we have a tremendous number of many visualization schemes to handle, multi dimensional data set. And of course, I know there's some extension to the parallel coordinate plot to handle, time variation. Yeah, but to tell the truth, for let me go to the which is the best? I don't know. Okay, here. So this is the underlying data set for bladder. Actually, this part, polarization and the polarization error, is strictly speaking, these are not scalar data set. This is a structured scalar data set. So I thought that, to come up with a new visualization schemes to handle these 4 parameters simultaneously as an ellipse, right? And then colorize each of the ellipse with the intensity and the color with reference to a color transfer function. We thought that this kind of new visualization schemes could be the best for, bladders. Of course, we could extend our concept so as to take advantage of other visualization schemes for high dimensional data set and time-varying data set. But please note that, time-varying multidimensional data set should be carefully visualized with our, promising visualization schemes. If not, so, the subsequent visual analytics do not, work very well, I believe. So anyway, today's lecture, I selected a very specific data set for time-varying multi-data set cases. So we, designed our own visualization scheme for the data set. But generalization is a very important topic of research. So I encourage you to do that for your own data set and more general cases. Extension would be welcomed by your research.
Okay, thank you. And also the next question is how to evaluate the quality of automatic feature extraction?
Yeah. Okay, good. Yeah, good question. Yeah, due to the shortage of time, I didn't mention about furthermore, case studies with the specialists from astrophysics area. So fortunately, we have many references to report the target data set in the past. Okay, so in such a paper described somehow the feature of the target data set with the traditional method. So the first challenge for us is to have exactly the same result, okay, to support their hypothesis with the previously published papers. Okay, so after that, so let me deepen our analysis to get more results. Okay, and sometimes our colleagues from the astrophysics area had their own original data set. Okay, so in the happy case, they could rewrite their report with the deepened analysis results in some cases. Anyway, any visualization, in visualization paper needs, ground truth, right? But astrophysics area is an exceptional area. As I said before, no one, no one can travel to see the real bodies located far from the Earth. Only option is to rely on the real signals emanating from the distant body, right? This is the basic feature of the astrophysics, astronomy. So I need to make a reference to the, all the journals to deal with the same target data set, the brothers, to compare our results with the results, reported in the previous papers. Then we are going to deepen our analysis a little bit further together with the astrophysics experts. So this is a start of our evaluation of our methods so far. Yes.
Okay, thank you. And also the question from the audience. It's mentioned that the zero query mechanism can be applied to a multidimensional time series data sets in other fields. Specifically, how can it be applied to other fields? Or what are the distinct advantages of this zero query?
Yes. Yeah, as I said before to another question. So I think, the vital part of our visual querying systems is that we need to specify the trajectory of the selected two variables. For example, yes, so yeah, maybe here, just like this, okay? So, and also we can assign some property of this kind of trajectory. In this examples, the two variables are Stokes plane variables, Q and U. And then you can, succeeded in deriving this kind of trajectory of light coming from the blazar, and added some property in this example, the intensity of light. Now, of course, you can assign the color data set onto this stroke if you rely on some texture-based multidimensional visualization scheme could be applied. Anyway, this trajectory is a vital part of for the construction of the query by sketch. Yeah, so if you succeeded in such a trajectory structure extracted from your own data, I think our method could be applied to your data set. Of course, if you have such a scatter plot from the two-dimensional selected variables correlation, maybe you should search for more appropriate comparison method. So let me say once again, so this kind of trajectory structure and adding the feature of the trajectory is a salient feature of our query by sketch system. So please consider your own case, whether our method can be applied to perform visual analytics on your data set or not. I'd like to have your report in the future somewhere. So, okay.
Okay, thank you very much. And the next question is how to take into account observation errors in the process of feature extraction?
Yeah, so error is a very, very important topic in in this application as well. Yes, so for example, so yeah, actually, so which slide is much better? So anyway, yes. So maybe you can see this kind of animation here. So as I said before, we can, tweak the best opacity transfer function, okay, to have the most meaningful appearance of the, time tube, okay? So any astronomer have a, intuitive feeling that the, how much, error can be embedded in each of the data samples. So by providing them with such a, interactive method to tweak the best opacity transfer function, so maybe we can identify how much, errors can be embedded in the actual set of data samples. So this is one way to, detect the, magnitude of the errors embedded in the data samples in a time to view. But I think we have many more mathematical analysis of the identification of the error embedded in the data samples, I believe. Okay.
Yeah. So, okay. So, thank you very much for the answered all the questions. And due to the time limits, so if all the audience, if you have more questions, you can communicate directly with the Professor Fujishiro, or you can, or you can contact with our CSIG-VIS technical committee, and I will forward the question to the. We will forward the question to the Professor Fujishiro. Yeah. Okay. Today, Professor Fujishiro, today we have more than 2,000 audience from
really?
Yeah, and the Zoom platform and Zoom platform, these two platforms. Thank you very much for your wonderful talk. And it's the end of this talk. And thank you. Thanks for the Professor Fujishiro, a wonderful presentation. And thanks all who attended today. So the next lecture will be on December 2nd at 9 o'clock morning. The speaker is Zhonghua Liven from University of Arizona, United States. The topic is neural representations for a volume visualization. See you next time. Thank you. Yeah. See you. Bye-bye. Yeah.